inefficient ways of actually building up a binary search tree and doing a various operations on that. This is the whole goal. This is the whole agenda of the whole session, where we are going to implement various operations that you can definitely go around if you're working on binary search. Let's talk about what typically a binary search tree is. Binary search tree is exactly like a normal tree that you built uh, in the previous session. It's exactly the same, but there are few changes you'll have to make in order to enhance the performance, where you say, okay, fine, retrieving the data becomes a little easy, or inserting the data becomes easy, or maybe deleting the data becomes easy, not for the developer, but definitely for the user, right? And we're going to talk about that. But these are the collection of nodes which are arranged in a very particular way. It's maintained. The binary search tree is really a maintained tree, where you typically will always have to think about, okay, fine, I have to maintain this binary search tree. Every time you're going to do something, every time you're going to keep this in mind, mark my words, what I'm saying right now, that every time you'll be doing any operations on this tree, you'll every time will have to think about, okay, fine, I've arranged the data in the tree in certain order, and this is the order which I do not want to break, right? There are a few properties of the BST that should not get violated if you're working on any of the operations, maybe inserting or deleting or updating and something like that, right? What is a binary search tree and what makes this unique is it has three typical properties. I call this as three typical properties. These, you can cater this as onto two. One thing is pretty much common that you have seen as of now. If you're going to going around and building up a tree, what do you typically do? What you do is you just go around and randomly arrange the data. Uh, I just hope everyone can hear me up. Is the audio okay? Guys, is the audio okay? If the audio is okay, just give me a yes. Yeah. Aradhya, I highly recommend you to check your internet connection. From my side and from other people's side, I just hope everything is going good. All right. So let's talk about that. What have we done and what are the differences? What do you used to do? You typically used to, you used to have a bunch of data. Let's say you have data, let's say 10, 20, 30, 40, and maybe let's say 50, right? This was the data. This was the typical data which you wanted to store inside a inside a BS, a tree, a normal binary tree. And what you used to do, something like, let's say the root is 10, the left is 20, the right is 30, the left of 20 is, let's say, 40, the right of 20 is, let's say, 50. Now, if I talk about the arrangement is really, really random, right? I'm storing the data anywhere. But what I actually need to do is actually to arrange the data so that retrieving of these data becomes really easy for me, right? One thing you need to keep in mind that every time you'll be inserting some certain stuff up in the BST, you have to be very, very, very careful when you're doing something like this. Let's talk about the properties. Let's talk about what these properties of your binary search tree is going to give you. Okay, let's say I have a tree. Okay, just have a look on this tree, and I'm just going to ask you a few something. I'm definitely sure that you might have seen this tree somewhere before, right? If let's suppose if I build a tree, something like this. If let's suppose I have a root, and I give the value of the root as, let's say, 60, then I go around and say 30, then I go around and let's say 70, then I say, let's say 10, then here is your 40, and let's say if I say let's say 65, and let's say 100. Just have a look on this tree, and then I'm going to tell you that there are few things that I've done and I've kept in mind while building up this tree. Just have a look on this first. Go around onto the node, each and every node, and just figure out that something is special about this. Something is really, really special about this. What is it? Somebody in the left is lower, good, and right is higher. What is Abhinav trying to explain you guys over here? He's trying to say that every time you choose any node, irrespective where that node is, yeah, it's a BST. What is making this as a BST? This is making up a BST where you have to keep two things in mind if you're trying to insert something in the tree. First, that every time you're inserting, the left of that tree, the left child is smaller value. And second thing you need to keep in mind that the right child is typically the greater value, right? Now, in this case, what's typically happening? Now, go around onto any node, any node. If let's suppose if I pick this up, 60. If I have a look on the left child, which is 30, I can definitely say 30 is less than 60, but the right child, which is typically 70, is greater than 60, right? And this property, these two properties typically hold for any of the nodes that you can come across with. If let's suppose if I'm talking about the 70, 70 has a left of 65, which is less than 70, and has a right of 100, which is definitely greater than 70. Yes? Guys, is this cool? Is this okay? For the people who are new to BST, is this okay? And even for the people who have done BST before, this is what you have learned, right? This is what you have learned. Yeah, this is what we're going to talk about. This is what we're going to build. And we're going to talk about that how retrieval becomes easy, how the becomes easy, and how the arrangement, later arrangement in this tree becomes easy. We're going to talk about that. But as of now, let's go back to this. So what a binary search tree is, it has few properties, which I've told you. The left subtree of the node has a key which is less than or equals to its parent node. What I said, that it is going to contain data. If let's suppose if you just have a look on the 60, every node which is at the left of 60 is always going to be less than the value of the root node, right? So if you just talk about this root 60 and you just have a look on the left subtree, which is 30, 10, 40, all the three values are typically less than 60. And vice versa, the right subtree of the node has always going to contain all the greater values as compared to the parent node or to the root node. If you just have a look on all the values at the right subtree of the 60, it's going to find out 65, 70, and 100 definitely are the values which are greater than 60, right? The next thing you need to keep in mind that while searching, the desired is compared to the keys. BST found that the associated value is retrieved. We're going to talk about that. And as of an instance, I'm just going to not discuss that last point. I'm going to discuss that last point at the end when we are done building the binary search, and that will make more sense, right? But as of I'm going to cater that last point out, right? Let's move ahead. Let's talk about a few different things. So if you just talk about one of the very classic example, this is one of the classic examples that you can see in front of your screens, which is, let's say 5, and all the data which is left, which is 1, 2, 3, which is less than 5, and all the right part which is greater than 5, right? All the 9 to 25, all the values that you can think of is greater than 5, right? So this is what I can call any BST. So any of the tree which is going to follow these two properties is definitely going to make this tree as a BST, right? Okay, cool. So if you're good to go till here, just give me a quick yes so that we can move ahead. Shall we? Should we go ahead and start building this up? Okay, so let's not waste time. This was pretty much all the theory that you needed to have, because for the people who might have joined for the last session, they would be will be able to cope up with all the things that we're going to talk about next. Okay, so let's go ahead. I'm going to go around onto IntelliJ. Keep that in mind. I'm going to make use of Java. You can go around and code it almost onto any of the programming languages that you want. Okay, I'm going to go around with Java, and you'll realize that syntax is almost the same. There is nothing hard and fast with the syntax, right? So I'm just going to build a new project. Going to select Java. I'm working on Java 8. You can work around on any of the Java version that you want. And I'm going to say create the template for me. I'm going to say next, and I'm going to give this name as, let's say, webinar. Okay. All right, so it's going to build all the components for you, and we'll be almost ready to code that up. Okay, cool. C++ is not going to happen today, and the reason is that I do not have a compiler for that. I typically will have to go around and download Xcode, and it's going to take a lot of time because it's around 3.5 GB, and I presently do not have it right now. So we'll have to go around with Java. I just hope everyone is comfortable with Java. online compiler does not give you so much of a leverage where you go around and talk about different things. I'm not gonna go around with. Okay, so last time what we did was we had a look on and everything. We are going to, as of now, we're going to stick with Java. You can go around and talk about any of the things that you want, but I'm going to stick around with Java. Okay. Okay. How many of you found actually a lot of differences between the syntaxes if I talk about C or C++ or maybe Java? How many of you feel poster? What poster? I didn't get you. See, at the end of the day, syntax is not going to matter. I'm going to explain you each and every syntax. It's see, try and understand this as a new opportunity of learning of a new language, as a new programming language. Java is going to be definitely is going to be new for you, but you're going to realize that, okay, fine, you can also do competitive programming and data structures on Java. Java is going to help you a lot, guys. It's definitely going to help you a lot. For the people who find that, okay, fine, I need to go around with C and C++, there isn't much differences. Even for the people who might have joined for the last session, you might have realized that I wrote something and it made absolutely the same sense as we used to do in C and C++. Right, guys? Other people? Except for the pointers, everything is going to remain same. And for the people who might will get stuck somewhere between the pointers and something like this, I'm definitely going to explain you that in this session. But as of now, I'm just going to keep it to Java because that's the thing that we are going to have a look on as of now. Cool? Everyone is okay with that? There is no much difference in the syntax. I'm going to explain each and every syntax. Don't worry about that. All right. Should we go around and build something up? Shall we? Is everyone ready? Is everyone here with me? Yeah. All right. So let's go around and do something up. Okay. We are going to build what? We're going to build a binary search tree. We are going to talk about that, how your binary tree is absolutely different as compared to binary search tree, and you're gonna get a lot of operations that you're gonna realize, okay, fine, yeah, this is really, really cool, right? And we're gonna talk about that. So what I'm going to do, I'm gonna create a new Java class. I'm gonna right click onto here. I'm just gonna go to Java class, and I'm just gonna call this as, oh, sorry, grab this up again. I'm just gonna call this as binary search tree, right? It's exactly like creating up a new file on C and C++, and you're just going to name that up, right? All right, so let's go around and build that up, okay? Now, what do we need and what we have done as of now for the previous session, what we have done, we have talked about how typically a tree is going to help out, right? For the people who have been working on C and C++, what you typically do is you first go around and create a structure for yourself. Which platform for Java? I love working on IntelliJ. You can go around with NetBeans, you can go around with Eclipse, you can go around with any of the platforms that you are. You are even okay to go around with VS Code, but I highly do not recommend VS Code for working on Java. The best compilers that you can think of is IntelliJ, because this is where professionals works on. Okay, a lot of developers are real-time developers who works on Java and work and build enterprise applications. They work on IntelliJ. This is one of the best IDs that you can get around. But I'm using IntelliJ, but you're free to work on any of the other platforms. Okay. So what we discussed as of now, or in the previous session, we talked about that rather than just creating up a structure in C and C++, what you used to write was you used to call this a struct node, and then you used to give the structure. What I'm going to do is not going to give any structure, but what I'm going to do is I'm just going to comment that out so that you can keep it out for the reference. What I'm going to do is going to actually create a class called as node, and you're going to realize that there is no much difference. Okay, what I'm going to do, I'm going to create a class called as node, which is going to contain what we have talked about this. Because it's a binary tree, it's going to contain certain things. What it's going to contain, it's going to contain the data which you want to store, which I'm calling this as a for key. You can keep it the name in anything that you want. You can keep it data, you can keep it anything, but I'm going to call this key. Key is what? The data that we are saving in the node, right? And what we'll be having is node as left and right. Now you can keep this in the mind that I'm using the return type or the data type. This is typically a complex data type in Java. You can think this node as to be the reference pointers, right? These are actually reference variables, right? If let's suppose if I go around and create this up, okay, so I'm just gonna show you certain things, okay? for the people who are new to Java, I'm just going to show you something. If let's suppose if I say node equals new node, right? And if let's suppose if I just do, so I'll have to create. Or maybe I'm just going to give it this way. So, okay, so it's giving me an error because it's giving me anything because it's static, right? So if I just keep this as static, definitely it's going to give me everything. Cool. So if I just go around and do S out, and if I print node, and if I run this up, which is binary search tree, just have a look at what's going to give it back to you. It's going to give you a memory location, which is going to be looking like something like of a hexadecimal code. Just have a look. See, so it's going to give you this binary search tree, $node @7b1d7FFF. Everyone can see this output. Everyone can see this output down below. Everyone can see this output. So you can think of using pointers in Java, but in a different manner. Saying, okay, fine, I'm going to create a new class and I'm going to use it as a pointer. So you can definitely use it as a pointer. So what I've done is I've done this way. I've said, okay, fine. I wanted a pointer. So what I'm going to do, I'm just going to create a pointer called as, okay, so I'm just going to create two pointers called as left and right. And the type of these pointers are going to be node, right? So it's a node type left and right. That's what we're going to do. Right? And then later on, what I'm going to do is going to create a constructor. A lot of people would be knowing about constructor. I'm not going to go around this and talk about that because we have done that already in the previous session. So I'm not going to go around with that. But every time I'll be creating objects for this, what is going to happen is going to contain a key. And what it's going to do is initialize your stack memory. How it's going to do this? It's going to say this.key is equals to the key that you have mentioned up here. So if I just hover over this is a key which is getting passed when you're calling this constructor. And if you just keep on this key, this is the key which you have created in the stack memory, which is your int key. And what I'm going to do, I'm going to initialize this left and right to null as of now. I'm going to say this dot left equals this dot right equals null. As of now, I'm just going to keep this as null. And what's going to do that every time you'll be creating up a new node, what is going to happen, I'm just going to annotate on the same screen. What's going to happen is it's going to build a node, and this node is going to typically contain three different things. What? It's going to contain a left, it's going to contain a data, and definitely it's going to contain a right. Now, if you talk about this left and right, these are again node type. So it's going to act like a pointer. So you can keep this in mind. It's going to act like a pointer. And this is the data which is going to happen. And every time you'll be building up a node, what's going to happen is it's going to take the value. And let's suppose if I pass the value as, let's say 10, it's going to insert 10 in the key. And for the left and right part, it's going to keep this as null as of now because it's not pointing anywhere. So it's just going to keep this as null. I just hope this makes sense to everyone. This class makes sense to everyone. Is it okay? There is no as of a difference, right? So if you talk about differences, there are no differences, right? So you used to create what? You used to create structures out there. What you're creating here is going to be definitely classes because it's an object-oriented programming language. Okay. All right. So this is the thing. This is the stuff that's built. As of now, I'm not going to call this because I'm not going to make use of it. All right. So this was it. This was a node that we have thought about. Now, what we want. What we used to do initially was, okay, let's back here and talk about what to do. Initially, what we used to do, whenever we used to build, what we used to do was to just think of the data, which let's suppose is this. And potentially what we used to do was we used to call this as, let's say, root, and we used to call this as root.left, and we used to call this as root.right. And every time I wanted to insert something, I have to give the value every time. Now, what do I want? I want to keep the things in mind, and that's okay, fine. Every time I'm going to give a value, my tree should be built automatically. Is the problem statement clear? That's what I'm going to do. And what's the first thing that I'm going to do when I talk about BSD? Yeah, that the problem statement there was that every time I had a binary tree, I specifically have to, in the main method, I always used to say root.key equals 10, and then I used to say root.left.key is 20 and stuff like this, right? But now what do I want is typically a function which is going to take the argument as of for the key and going to build the tree automatically for you, right? So this is the thing that we're going to do. This is the first operation that we're going to have a look on, that what it's going to do is going to take a value key and going to insert that app back onto your what? Onto your binary search tree. This is the goal. This is the thing that this is the first step that we're going to have a look on right now. Okay, everyone is ready. Everyone's here. Should we go around and talk about this? Yeah. All right. So the next thing that I'm going to do if I go around and code here is going to create a global variable. I'm going to create a global variable. Which global variable I'm going to create? I'm going to create head. And what this head is going to do, it's going to refer to the start of the BST. Okay. So it's, you can consider this as maybe top for the stack, or maybe what you call this as the head pointer of your linked list. This is exactly the same. I'm just going to call this as root, and this root is going to do the same stuff for you, which is acting global variable. This is always going to keep a track that where my tree is actually starting from. This is the starting point of my BST, and this is a global variable that I'm going to create. So I'm just going to call this as, let's say, private, let's say node type. Again, node, I'm going to keep this as node because I need a reference. I'm just going to call this as root. Pretty cool. Yeah. So I've created up a global variable. I'm going to call this as root, which is going to refer to the first and the starting node of my BST. Okay. And next thing what I'm going to do is actually create the constructor of the class, or the constructor of the BST, which is the upper class, which is this binary search tree. This is a class, right? This class is containing another complex data type, which I'm calling this as a node. But what I'm going to do is going to create and mention the constructor for your binary search tree, which is going to do what? Let's have a look. So I'm just going to say binary search tree, and this binary search tree is going to allocate this root to null, which is going to say, okay, fine. The moment I'm going to create a binary search tree, my binary search tree is going to be empty. Why? Because root is pointing towards null, saying that, okay, fine, I do not have any starting, which means that the binary search tree has not been created as of now. Make sense? Does this make sense? So the constructor, the moment I'm going to create the object for your binary search tree, it's going to initialize your root, which is what? Which is a reference to the start of the BST. It's going to say, okay, fine, it's null. There is nothing inside the tree, which is up right now. But initially and gradually, we're going to contain certain data inside the BST. Why do we keep root as private? You can keep this as private because, okay, so let's not keep this as private. It's completely fine. Don't keep it as private. It's completely fine. Yeah, it's just an access modifier because you do not want to give access of your root to multiple other functions. So generally you keep this as private, but again, if you do not want to keep this as private, completely your call. Nothing hard and fast. Make sense? Can we go ahead? Anything that you want to ask as of for now? If you're good to go, just give me a yes so that we can move ahead. Quickly, everyone? Yeah? All right, so this is the basic layout that we have built. And two classes need why. All right, so first thing, okay, so you can think about these classes as the things that you're going to build. Okay, let's keep this way. What are you going to build? First of all, what do you need to build? You need to build a tree. This tree is typically going to look something like, oh, sorry. It's going to look something like this, which is going to be the whole tree. And this whole tree is consisting of what? Aradhya, this whole tree is consisting of what? This is I'm calling this as a tree. This is what I'm calling this as a BST, right? I'm building this BST, and this BST is consisting of what? What is consisting of? The BST has what? Nodes, exactly. So just think about, now just have a look on this code now. What do you have? You have the whole tree, which consists of nodes, right? So what do you have? A class, a bigger class. We're calling this as a binary search tree. And this binary search tree as a class is containing another class, which we're calling this as a node. Why? Because the binary search tree contains a lot of nodes inside this, as simple as this. Aradhya, does this make sense now? Classes, the outer class, which is your binary search tree, which is going to contain a lot of nodes inside the BST, right? So this is why you're creating up another class inside the node. Yeah. All right. So everything is all done. Everything is all sorted. What we have done, we have created up a node, a basic layout, a basic class, a basic template for that how your node is going to look like. This is going to contain a key, two reference variables called as left and right, which is going to contain the addresses of your left child and the right child. And then a small little constructor that every time you're going to call this node constructor, you have to pass this value. It's going to build a node for you, and it's going to keep the key as a key that you pass in, and the left and right has to be null, right? As simple as this. Now, what we're going to do here, we're going to perform various CRUD operations. We have talked about CRUD operations before as well. And here, your CRUD operations are going to start from. So these are the CRUD operations that we're going to talk about. Okay, the first CRUD operations that I really want to focus on, the first thing that we're going to build as of now is going to be insertion. We're going to talk about the insertion in BST. Should we go ahead? Should we talk about the insertion part? Should we go ahead? Okay. Now, everyone, if you're doing something and you want to make something out of this session, I highly recommend you to just drop everything that you're doing for a minute and just have a look on the concept that I'm going to tell you up here, how you're going to insert something in the BST. Okay. The thing that I'm going to talk about is nothing to do with the syntax. This is the thing that you'll have to write in C. This is the same stuff that you're going to write in Java or maybe Python or Spring and anywhere, right? This is the whole logic part, which I'm going to talk about, which is the insertion logic. How you're going to insert a node inside a BST, irrespective of what framework or what languages you're working on. Okay, you're going to insert what? You're going to insert a node in the BST. How are you going to do that? Let's go around and have a look at what have we taught. One thing that we know is what you need is a root first, right? Depending on that root, where your tree is typically starting, you will have to figure out that where is the next thing is going to go, right? What do you need first? First you need is root. Root, where your tree is typically starting from. This is what you need. Every time you're going to insert something, what you need is the root, because that's where your tree is starting from. So what I'm going to write, I'm just going to create a public void. As of now, I'm just going to keep this as void so that you don't get confused. I'm just going to call this public void. I'm just going to say insert key, and I'm going to pass is a root, which is going to tell where my BST is going to start from, and a key, which is going to insert. As simple as this. Two parameters, a root, which is going to tell, okay, fine, this is where your BST is going to start from. And the next value is going to be the actual data that you want to store inside that key. All right. Pretty much happy with this. Nothing hard and fast, right? Let's talk about this. Let's talk about the logic now. Now, what do you need? Now, think about the worst case scenario. Accessible to the whole class. Why are we passing it again? Yes, it's accessible. It's definitely accessible. The reason I'm just going to keep this as root, yeah, it's a global variable. Definitely accessible. Correct. Why I'm keeping this up, I'm just going to hold this thought for a minute. I'm going to tell you that why I'm doing certain stuff like this. I'm going to tell you this. This is all the properties. You might have heard about OOPS, right? Object-oriented programming paradigm. It's a different paradigm where you say, okay, this is abstraction or maybe polymorphism and stuff like this, right? So keep this thought for a hold. I'm going to tell you that I'm going to pass this up every time. Though I've done in the previous session as well, people would be knowing that what I'm going to do next. But as of now, just let's keep this node up here. It's just a local reference to this node, this root as a node, right? But as of now, I'm just going to get back to this question because I'm going to explain you that why I'm doing certain stuff like that. All right, so what do you have? You have a function which is key, right? Now, everyone, just listen to me. What is the first and the worst case scenario that you can think of if you have a tree, and how you're going to start building up a tree? Just think about that. How are you going to start building up a tree? What is the first node which is going to pop up? If you're building a tree from scratch, if you're saying I'm going to build a BST, how that BST is going to build, which is the first node which is going to pop up if you're saying you have to build a BST? Think about it. Just listen to the question very carefully. If I'm saying that, okay, fine, you need to build, good. The first node that I actually need to build is going to be root, right? The root is right now null because that's what I have done, because I've said to the compiler that, hey, listen, the moment everyone just calls this constructor called as binary search tree, what you need to do is initialize this with the root. And the first case scenario is going to be this. This is a case number one. This is what you're going to say when your tree is empty. When your tree is empty, saying when the tree is going to be empty, when your root is going to be, your root is going to be null, right? And this is the case. This is the stuff which you're going to do when you're inserting the data for the very first time. You'll have to check that whether or not my root value is null or not. If it's null, you'll have to appoint that particular node as a root node and keep all the other nodes as the ordinary nodes, right? Do you agree with me? Because this is the first thing that you're going to do. And how are you going to check that up? You're just going to say if this root is null or not. And the moment it's null, you get the point. Okay, fine. Yeah, this BST is typically empty right now. I do not have anything inside this BST, but I'm going to insert something else inside this. But as of now, the root is null. So if the root is going to be null, what are you going to do? You have to create a node. You have to create a node and appoint this as root. Yes, this is what you're going to do, right? What are you going to do? If your root is null, you'll have to create a node for itself, and you're going to call this node as the root node. Yes, this is the first step that you're going to do if you're inserting something up. Good with this? Should we go around and do something? Guys, yes? So what I'm going to do, now just have a look. What I'm going to do, very, very simple. You can do exact same stuff on C and C++. What I'm going to do, I'm going to target onto the root. The root is containing the first starting of your BST. And I'm just going to say equals new node. And I'm going to pass, let's say, whatever value that I want. And the value here is this key. And I'm going to pass this key up in here. Does this make sense? And then what I'm going to say is S out. I'm just going to say data. Oh, data. What data? The data key has been inserted successfully. Cool, right? And then I'm going to return this root. And then I'm just gonna remove this up as node. Anything weird that I've done? Anything that anyone feels that this is really, really weird? Anyone who didn't get that what I did right now? If you're good to go till here, just give me a yes, a quick yes, so that we can move ahead. Yeah. Nothing hard and fast. Nothing hard and fast. It's gonna give me an error, missing the return statement. Nothing hard and fast. We're gonna talk about the return statement as for now. But what we have done, what's the whole agenda? That what we're doing is building up a BST, and in that BST, return value the root to. Where we're going to return the root value to? You're going to return the root value where it's going to get called from. Abhi, just give it a thought. Abhi, filhal ke liye don't think in a very wide manner. You can keep this as a void, jo maine initially rakha tha. You can keep this as a void for the initial part. But slowly and gradually you'll realize, okay, fine, yeah, this is why I'm doing certain stuff. Why? Because next thing that I'm going to write in the code is going to do everything for you. All right? Guys, should we move ahead? As of now, just think this as a syntax, or what I've done is kept the return type as node and returning the root every time. Now, irrespective of who's gonna call this function and how it's gonna retrieve the value, that's a different story. But as of now, what I've done is kept the return type as node and returning the value of the root every time I'm doing something. Make sense? Good to go. Just give me a quick yes so that we can move ahead quickly. Again, if you have doubt, don't feel embarrassed at how will I'm going to, put the doubts. It's fine. Even if it's a tactical doubt, it's completely fine. And I'm requesting this from every student who's sitting in the session. If you're good to go till here, just give me a yes so that we can move ahead. Quickly. Yeah. All right. What we have done, we have built first node and kept that up and said, okay, fine, if my if my tree is going to be empty, what I'm going to do, I'm going to build a new node. I'm going to call that node as the root node, right? This is case number one. If your tree is empty. What if your tree is not empty? What are you going to do then? Case number two. Tree is not empty. Tree is not empty. It was built already, because the kind of like the root that you got as a parameter, it says that, okay, fine, yeah, it's not null. So the condition of root getting null got false, so it needs to go somewhere else. So case two, that's what we're building. We're saying, okay, fine, the tree is not empty. Rather, the key that you have passed is maybe, let's say, less than root. Yeah, remember the two properties that we had to talk about when we were talking about BST? You typically can have only two options. Either that the value of the root is going to be either less or either greater than the value of the root node. And what you have done, you have just created up a root node and contained the value inside that root and said, okay, fine, I've built up a new root. And every time there will be a new insertion, where every time this function is going to get executed once more, the value of the root is not going to be null. It's not going to be null because you have already built this root. And case two is saying, okay, fine, yeah, the tree is not empty, but the value that you're getting passed is going to be less than the root, because every time you're going to insert something up inside that tree, you'll have to check the value that you're passing is either less than the value of the root or greater than the value of the root. And that's typically what I said. Every time you're going to do any operations on the BST, these are the true properties you'll always will have to keep in mind, so that the properties of the BST does not get violated. Case number two, tree is not empty and the value that you're passing is less than the root. Seems okay to everyone? Seems okay to everyone, guys? Quick. Yes or no? All right. Okay. What is the next case that you can think of? Okay. First case, the tree is empty. The tree is completely blank. Case number two, if you're inserting something, that key is less than the root value. What could be the another case that you can think of? Any other case that you can think of? I'm not going to go inside the coding of case two. What I'm asking is there any more cases that we actually need to cater if you're inserting something up? Yeah, valid point. Whereas saying, okay, fine, yeah, the key could be greater than root as well, right? Everyone, do you agree with Ishita? Yeah, do you agree with Ishita? That this is another case that you'll have to cater on. The case number three. So the case number three is going to be what? The case number three is going to be tree is definitely not empty, because that's the thing, because the if statement got violated, and says the case could be that the key is technically greater than the root value, right? Can you think of any other cases? Any other cases? That the key was greater than the root, less than the root. Any other cases that you can think of? Quick. Yes or no? Just yes or no. Very good. So the people who said that key equals the root, yes, could be a possible case where you're saying, okay, fine. Ishita said, okay, fine. So this could be a case where I'm saying, okay, I'm filling something in, and I'm not. That could be a possible situation that it's already available in the BST. Yes or no? Guys, quickly, yes or no? Yeah, this could be a possible situation where I'm saying, okay, fine, the value could be less or greater or equal. There could be no other possible solution. Now just listen to me very carefully. This is really important from the I'm saying project point of view. It's really important from the interview point of view. What I'm going to say, just open up your earlobes and listen to me very carefully. In the BST, you do not contain any of the duplicate data. Now think about if I cater this case on, where I say, okay, fine, I have a key which could possibly be equal to the value of the root node. And then I create up certain operation and insert that somehow in the tree. Will it not contain duplicate elements inside it? Just yes or no. If I say that, okay, fine, I have a key which has exact same value which contains in the root node, and I do certain operation and somehow I insert that value in the root or in the tree, will there or will there be not duplicate values in the BST? Yes or no? Quickly, yes or no? If I say, again, I'm repeating the question again. If I say, if I cater this case up where I say, if the key is equals to the root, then what's going to happen? I'm going to insert that node again back in my tree. What's happening is the root and the new key is typically having the same values. And what you're doing, you're inserting the same value again back onto your BST, which is going to do what? Which is going to, yeah, so that should not be inserted in the BST. And that is what makes your BST so special. Very, very important, very, very important properties. Any BST does not contain any duplicate elements. Very, very important. So can you think of any of the other cases apart from this where you're saying, okay, fine, the tree is empty and the key is less than the root value, and the tree is not empty, and the key is greater than the root value? Any other cases that you can think of? Yes, no? Yes, no? Quickly. Can you think of any of the other cases? No. All right, so let's go around and build these up. And we're going to see that, okay, fine, is it working okay or is it not working okay? Okay. The case two, when the key is less than root. Really, really important. And this is what we have discussed in the PPT. What happens when the tree is not empty and the key is less than the root value? Where should this node go? If you're talking about BST typically have only two things that you need to keep in mind. If the value is less than the key or to the root, where does it needs to go? It needs to go to the left of the tree. So I'm just going to call this as left of the BST, right? And similarly, if I talk about this, because the value is greater than the root node, so it typically should go to the right of the BST, right? And how you're going to do, and now you're going to realize that why have I kept this as node? What I'm going to do, I'm going to say that, hey, listen, every time I'm creating up this or inserting any of the elements inside this, I'm going to check that up. I'm just going to say if the key is, let's say, less than the root dot key value. What's going to happen next? What's going to happen if something happens like this? In this particular scenario, what I'm going to do is typically going to say that, hey, listen, every time there is going to be certain stuff up where I'm saying key is less than the root, what you need to do is going to go onto the root dot left. I'm going to say insert key. I'm going to pass what? The root dot left. I'm going to paste this key up. Does this make sense? This small little line which I've said that, okay, fine, if the root is the smaller value, oh, sorry, the key is a smaller value than the root, then that key is needed to be pasted in the left hand side of the BST. So what I've done, I've created up a recursive function, and this is the recursion happening in place where I'm saying that, hey, listen, this key, this new node which I'm going to create is going to get created onto the root dot left. And similarly, what I'm going to do is going to check else if what? Else if the key is, let's say, greater than the root dot key, then what I'm going to do is going to say root dot right equals insert key root dot right comma key. Okay, be honest and tell me how many of you didn't get what I've written in the recursion part. I'm just only talking about the recursion part. How many of you didn't get the recursion part? Because this is what is most important to understand the recursion. I can tell it to you conceptually, but you actually have no idea what's going behind the scenes if you're working on this kind of like recursive methods. Anyone who has got the idea, got the part that what we're actually trying to do up here? Anyone? Very, very crucial, very, very important part. Anyone who has got that what's happening in the recursion? Anyone? What is getting stored in the root dot left? Good. So now you're coming up. Root equals key won't be considered. Yes, it won't be considered because we are not going to cater onto the duplicate values. That's what we have talked about. we are not going to contain any duplicate elements in the BST. So this is the case. Why are we taking root.left or right as a parameter? See, now listen to me very carefully. Everyone, just pay attention. There were two questions that you definitely asked me up. First question was, why are we taking root as a parameter? Answer is this, because I wanted to make use of recursive methods. Second thing you guys asked me was that why are you saying that it's going to return a node value? And the answer again is because I wanted to make use of the recursive method. Guys, yes, no, no, yes. Does this make sense? Though I'm not talking about the recursion part, I'm going to explain that how this recursion is going to happen. But as of now, there were two big problems that you had. First problem was, why are we taking root as a parameter? Well, the answer is because I have to make use of recursion. This is where I'm passing root.left. The second question that you had was, why do you have a return type called as node? Well, the answer again is recursion. Now, how many of you actually got that what's happening in the recursion? Be honest with this. Just give me a yes or no so that I can explain you in a better way. And this session actually means a lot to all the people. Just give me a yes or no that what's happening behind the scenes and what's not happening behind the scenes. Do it real quick. Just give me a yes if you got the recursion. Just give me a no if you didn't understand that what's happening in the recursion. Can you show a dry run once? Definitely, we're going to talk about that. Okay, now, before I actually go around and dry run this code and talk about that how this recursion is going to happen, let's go around and test this code up first, right? So what I'm going to do, I'm just going to say public, let's say void, let's say in order, traversal. I'm going to pass node root, right? And if I'm just going to check if the node or the root is not equals to null, then I'm going to do what? I'm going to say in order traversal of root.left and then s out root.key and then say in order traversal root.right. I just hope nobody has any doubts in this particular function. We have talked about this function in very detail in the previous session. If somebody has a doubt, I highly recommend you to go around to this video again back. But how okay, so how many of you are comfortable with this small little function in order traversal? Guys, everyone is okay with this? Quickly, let's not waste time. Everyone is okay with this function in order traversal? Just taking a root node and doing something using recursion and doing certain stuff like this. Yeah, we've talked about this. We have dry run this in the previous session. For the people who have any doubt that how this recursion is gonna happen, you can go around onto the previous video and that's already there in the YouTube channel. You can go around and have a look on that. Okay, but now what I'm going to do, now just have a look. Now every of the dots is gonna get connected right now here. What I'm going to do, I'm gonna say that, hey, binary search tree, I'm gonna create a new object for you. I'm just going to call this binary search tree, which is a part of my com.demo. If you can just see that this is the file that I'm catering out right now, binary search tree. So I'm just going to say binary search tree. I'm going to call the object as BST equals new binary search tree. Now just have a look out here. This is the constructor call. Everyone, just pay attention out here. This is the constructor call. Everyone can see this constructor call? Everyone, just quickly give me yes or no. Everyone can see this constructor call. Binary search tree. And just remember that, what did I say? I said, okay, fine, I'm creating a constructor for your binary search tree that every time you're going to create a new object for your binary search tree, what's going to happen that it's going to keep the value of your root as null. So what's going to happen that everything is all done and all sorted. It created up an instance called as root, which typically is null right now. This is what it's doing for you. And now what I'm going to do is going to say bst.insert key. I'm going to pass root, comma, let's say, or maybe what I can do is, this is a better way of doing it. What I'm going to do is going to create an absolute new, I'm just going to say public void insert, and it's just going to say int key. And what you're going to do is you're going to say that when this happens, So what you need to do is you need to keep root equals root equals insert key. I'm going to pass this up with the root, comma, the key. Right? Then I'm gonna come here, and rather than just calling this insert key, I'm just gonna call insert and then pass 10. Or maybe not 10. Let's say I'm just gonna pass with, okay, let's keep this as 10. Then I'm gonna say bst.insert, and let's say I pass 20. Then I say bst.insert, let's say 5. Right? Now just talk about this. Oh, insert meaning insert. Now just have a look out here. Just guys, everyone, just give me one small little attention so that I can explain you that what's happening behind the scenes. Now see here. What do you have given as the values? What are the values? The values are typically what? The values are 10, 20, and 5. Just have a look what's going to happen. This is the first data which is getting transferred. And depending upon the things that we have built in the insert function, what's going to happen? It's going to read the first value. The first value is going to be what? The first value is going to be 10, right? So what's going to happen? It's going to build a BST, and the first value is going to be which value? Just have a look at what you have done in this 50 or 5. It's 5. Sorry, I'm so extremely sorry. This is 5. Sorry, 5. This is 5. Okay, so first value that you can cater around out here, if you just have a look on your insert function, the first value which gets over here when you say that root equals null, what is the first value which gets created out here? Depending upon the things that you have mentioned in the code, this 10 is going to be what? This 10 is going to be the, guys, this 10 is going to be which node? Tell me. The root node, right? So what it's going to do, it's going to take this 10 and going to make it the root node and say this is where the BST is going to start. Now the next data which is going to come up here, which is going to say now the root is already available in the BST, it's going to come here. It's going to say, okay, fine. What I'm going to do, I'm going to give the key as, let's say 20. It's going to say if root equals null, is the root null? Quickly, is the root null? No. So what it's going to do, as for the things that we have learned, it's going to do what? It's going to say key is less than root dot key. Well, that's not the case. Case is the case number 3, where your key, which is the 21, is greater than the root node. So what it's going to do, I don't know how it's going to do that, but somehow it's going to do what? It's going to paste this in the right hand side. And then what you're going to see is this key as 5. And what it's going to do, it's going to go back to this root and going to say, okay, fine, 5 is less than or greater than 10. Tell me, is it less than or greater than 10? Yeah, less than or greater than 10. So it's less than 10. So definitely it's gonna somehow pop up here. How? I don't know. But as of now, something is this what we have learned conceptually, and this is what we have coded. And let's go around and see that if I talk about that what is going to be the in-order traversal of this particular tree, tell me the in-order traversals. We have talked about this in-order traversals before. Tell me what's going to be the in-order traversal. The in-order traversal of this tree is going to be, guys, you're not responding quickly, just respond quickly. So as Rani said, the in-order traversal for this particular tree is going to be what? 5, 10, and 20. If I find the output as 5, 10, and 20, I can say that yes, the insert function is typically working exactly the same way how we wanted this to be. How? We literally have no idea. We're gonna figure that out. But as of now, this is what we know. Then this is what we need to do, right? So if I go around and run this up, let's see that what the in-order traversal of this is going to be. We're gonna talk about that. Oh, I didn't do the BST dot in order. Or rather, I'm just gonna say what? I'm gonna say, just 1 second. Just gonna come here and say public void in order. I'm gonna do what? I'm just gonna call this in order traversal and pass root. And then I'm going to come here. I'm just going to call in order. Right? If you go around and run this up back again, you could say that you're getting 5, 10, and 20, and that's what we expected the code to work upon, right? Now, as Ritika said, so what if both the values would have been less than 10? Let's say, if I say this would have been 7, let's figure this out now. Now, let's remove these up. Let's remove the drawing. Now, what are the things that you have? You have data as 10, you have data as 7, and then you have data as 5. Let's build this up. Let's say the first data is going to be a root node. So this is what your root is. This is why you're calling this as a root. The next value is 7. Where should the 7 go? Left or right? Just give me L or R quickly in the chat section. Where should this go? 7 should it go to right? No, it should go to left because 7 is definitely less than 10. So this is where it should come, right? And if I talk about this 5, where should it go? 5 is less than 10, so left of 10, and 5 is also less than 7, so it should typically come up here, right? And if I talk about the in order now, what would be the in order? The in order should be 5, 7, 10 if I'm not wrong. Got it? So the in order should typically be 5, 7, 10. And let's go around and run this up back again and see if this is working completely fine or not. And what I need to get is, let's suppose if I do this way, this should be giving me 5, 7, 10. Hold that thought, Aradhya, because when I'm going to explain you the recursion part, this is going to make all sense that what's happening behind the scenes. But as of for now, just keep this thought for the whole. Everything is going to get explained. Don't worry. Everything I'm going to explain from scratch. Don't worry about that. But I just hope you guys got an idea that, okay, fine, this insert as a function is working perfectly fine. Yeah, this is what we learned theoretically. And somehow we created something using recursion, but we actually do not have any idea that how that recursion is going to work. If you're good to go, just give me a quick yes so that we can start talking about how that recursion is going to give you some values up. Okay, all right. Okay, so what I'm going to do is going to give you every of the excruciating details up in here. I'm going to make certain things up here. I'm going to annotate here in the screen. I'm going to do certain stuff. Okay, just have a look. What do you have? Let's say what we passed before. Let's say we passed something like, let's take the very typical example. Let's say I passed 10, 20, and 5. Okay, this was the data. This was the input that we passed. This was the input. And somehow it built a tree, and somehow the in-order traversal came out to be 5, 10, 20, right? How did this happen? Let's talk about that. What happened initially? What happened? You had something of the value called as root, and root typically right now was null, right? Because that's what we have done in the main function. If you remember, when the moment we created something like what we created binary search tree. We created the constructor for your binary search tree. What did you do? You said that the moment you're going to create this constructor, you're going to initialize the value of your root to null, right? So right now the value of the root is null, right? What did you do? You said, okay, fine. First time when I'm going to insert some data, I'm going to check for the condition that if your root is going to be null, the root is null, saying, okay, fine, there is no binary search tree created whatsoever, right? There is no BST which was created ever. So what you're going to do, you're going to say that, okay, fine, this is the first thing which is going to get passed. What is the first thing which is going to get passed? The first data is going to get passed is going to be a 10. And this is what you're going to call this as a root as of now. 10 is root. This is the first data that we have given, right? Now, next thing what you have done, you have again called the insert function. You're saying bst.insert, and you're giving the value as 20. Now, what's going to happen? Just have a look. The root is a global variable, which is going to contain the value of 10. This is where your root is lying right now. Your root is no more null. It's 10, because that's what you have coded as of now, because it's a global variable, which is going to consist of everything, right? So now your root is actually pointing towards the node 10, right? And what do you want to insert? You want to insert 20, right? Now, the moment you're going to come here, it's going to check if root is equals to null. Is root null? Quickly, is the value of root null? No, right? what it's going to do, it's going to say if, now it's going to check the next condition because this condition got violated. It's going to say key is less than root dot key. Is 20, the key is less than root dot key, which is 10. Is 20 less than 10? No. Else if I say the key which I'm going to insert, which is 20, is greater than 10, definitely it is. Now what it's going to do, it's going to shift the value of root, this particular root, to root dot right. Now it's going to say what? Initially, if you remember what I've done, if I just expand this up, if you remember, the moment I create this, I say that, hey, listen, you inserted 10, left is null, right is null, right? This is where I can call this as root dot right. And what I'm doing is I'm saying, hey, in root dot right, perform the insert key method or insert key function, which is going to take the value of root as root dot right and going to create a new key. But if I talk about root dot key or root dot right, what is the value of root dot right now? Quickly, everyone. What is the value of root dot right? The value of root dot right initially is null. How do I know this? I know this because this is the constructor that I've created, that every time you're going to create a new node, you have to keep the left and the right as null. And this is what is happening. I just hope this makes sense to everyone, what I've done. Guys, yes or no? Yeah. So what's going to happen is, it's going to come up here. It's going to say, okay, fine. You're going to insert something, insert inside this. Now, what is going to happen is, it's going to say root dot right. In root dot right, insert the key root dot right. And then again, this insert key function is going to trigger up, but the value of the root will get changed to root dot right because that's what you have passed in the recursive function. And now every time wherever you're going to see root, that root will get replaced to root dot right. So if root dot right equals null, is root dot right equals null? Well, turns out, yes, that's the case. Guys, are you getting what I'm trying to say? Because this is what you have passed in the recursive function. So in the recursive function, insert key will contain the value of root as root dot right, because that's what you're given as of now, right? So it's going to say if root dot right equals null. Well, yes, that's the case. So what's going to say? It's going to say, okay, fine. What you're going to do, you're going to create a new node because that's what you're doing. You're going to say root dot right equals, because this is root and root will get replaced to root dot right. So it's going to say root dot right equals new node. So it's going to not contain null anymore. In the root dot right, it's going to contain a new node and it's going to say 20. But because you have given the constructor, so it's going to say that the root dot left dot, root dot right dot left is going to be null, and the right part of this new node is also going to be null. I just hope this makes sense now. Guys, now is it making sense of how the recursion is going to happen? Everyone, other people? Now let's go around and insert this 5 back. Let's go around and insert this 5 again. 5, now it's going to be a quick recap. Just everyone, just pay attention out here. If let's suppose if I want to insert 5 as a member. So what is going to happen? You're again going to call insert function, right? You're going to give the value of the 5 in the insert function. And what you're going to say? It's going to say root. Is the root null right now? No, the root is not null. The root is 10 right now. Still it's 10. Then it's going to say, okay, fine. If the key is less than root dot key, it's saying, okay, fine. If 5 is less than 10, is that the case? 5 is less than 10. Guys, going to come here and gonna check that if your key, which is 5, is less than the root. So 5 is less than 10. Well, yes. So what's going to do? It's going to say root dot left. In the root dot left, what you're going to do? You're going to call a function called as insert key. You're going to pass root dot key, a comma. It's going to pass a new key. So it's going to happen. So in the root dot left, this is going to call the function back again because that's the recursion that's going to happen. So root is going to get converted to root dot left. So now it's going to come here and say if root dot left is null. Well, yes, right now it's null. So what it's going to do, it in the root dot left is going to again create a new node, something like this, Gonna contain 5 inside it, gonna keep this left as null, right as null. I'm going to appoint this to the left part. I'm gonna say system.out.println data 5 has been inserted successfully. Right? Now, if I go around and run this back up again, I want to show you something that has really happened or not. See, first, what data got inserted? First of all, your data 10 got inserted, the way we predicted the insertion to happen. So first, this node got created, the 10th node got created. Then the 7th of the node or 20th of the node got created. And then at the last, the node 5 got created. And this is how your BST is gonna help you build a tree out of which you do not have to worry about that this data is going to go where, or to the left or to the right. Depending upon the value, you're just gonna predict that where this value is going to go. If you're good to go till here, just give me a big yes so that we can move ahead and talk about other things quickly. If this recursion makes sense, give me a big yes so that we can move ahead quickly. Other people? Where are the other people? Quickly, quickly. Aradhya, nahi samajh mein aaya? It's fine if you didn't get it. You didn't get it? You didn't get it? Okay, you mean you got it. Okay, got it. So this is how insert function is in a nutshell. Though seems like to be there is nothing much to have a look on. Well, turns out at the back end, a lot of things are going around. And this is the same code that you're going to write in your C and C++. And this is the same exact code that you're writing in Java. And this is the same code that you're going to write in Python or even in whatsoever language that you're working on. Should we go ahead and talk about one of the other operations as well? Should we go ahead and talk about that? One more operation, which is the most crucial operation in your binary search tree. Should we go ahead and do that? Cool. So let's do that. I'm going to create a function called as search, which is going to get any value. I'm going to pass that value. And depending upon that value, it's just going to tell me that whether or not this exists in the BST or not, right? This is the goal. This is the key step. Okay. Now, what I'm going to do, I'm going to create a search function. Now, in that search function, what's going to happen if you talk about search, how the search is going to happen? Anyone? Anyone? How is the search going to happen? Any idea? Any idea? Think about the things that you've learned as of now when you are doing a kind of like an insert function. The given element will be compared to the node and directed to the left or the right. Okay, all right. Let's go around and build this up then. Okay, how? Let's say I'm just gonna say public. So this is the second thing that we're doing is the search operation. So in the search operation, what I'm going to do is gonna create a function called as public. Let's say I'm just gonna keep this as let's say void. I'm gonna call this as search. Okay, and in the search, what I'm going to do is going to pass a value which is going to be key, and then I'm gonna call a function called as search. SEAR search key, which is going to take the node root and a int key. Okay, so you'll have to go around and build this up. Where is it? Did it called build somewhere? Oh shoot. What I'm going to do, I'm just gonna say public node search key, which is gonna contain what? It's gonna take a root node. I'm going to contain a key. and then something's gonna happen. Okay, what's gonna happen? Let's talk about that. Something's wrong. Oh shoots, what I'm writing. Sorry. Right? Just passing these values up. Now, what are you going to do? Now, just everyone, just pay attention. There are three cases that you need to keep in mind, right? The first thing, if let's suppose if you have a BST, let's talk up this way. If let's suppose you have a BST, what are you going to do first? Where are you going to start the comparison from, or where are you going to start the search from? The very basic thing. Root. What I'm going to do, I'm just going to say case number one. So if the key that you're going to pass is equals to root, how about that? So if your key, or maybe I'm just going to say key equals, oh, sorry, your key equals root dot key, then something is going to happen. What? I don't know. But don't you think something is missing around here? Anyone? Just think about one of the corner cases that I missed as of now. This code is going to break somewhere. Definitely going to break somewhere. Can anyone talk about what's wrong that I've written? Okay, so I'm just gonna say return, and this is gonna say root. Anyone could think about if the key does not exist. Abhi filhal ke liye, I'm just gonna say if, let's say there is a BST and you have a key. Will this work? Just think about this particular case. We are saying you might have a root, and okay, so let's not waste so much time. If let's suppose if I say if, chalo, let it just like be. I don't want to confuse you anyways. So if I say if your key equals root dot key, so it's just gonna return the root, right? This is what I want. What is going to get returned? A node. So what you're returning is the root because the key got found at your key dot write. Else, what's going to happen? You're going to take up a new if. You're going to say if your key is, let's say, less than root dot key. How about that? What are you going to return? You're going to return search key, and what you're going to pass is going to be root dot left. I'm going to pass the same key. Yes or no? Guys, yes or no? Yeah. And same stuff. If let's say key is, let's say, greater than root dot key, what you're going to do is technically return search key, and what you're going to pass is root dot write. I'm going to pass this key. Simple. Okay. Now let's call this function up. But the search function should typically give you the value saying yes, the value is present. If no, it should not give you the value. Right, so say if it's gonna return the value, right? So if I say public void search, so it's gonna say search key root dot key, right? So what I can do is what could be done? I'm just gonna think of one very small little problem statement because I don't want you guys to get confused. I'm going to write a very simple piece of code. So if let's suppose if I do something like, just give me 1 second. If let's suppose if here I'm saying that it's going to be of the type node, but I want to print the value that yes, it exists in the BST. So what could I do? Maybe I can just say maybe for let's suppose, okay, fine. I'm going to search the value, right? So if let's suppose, how about if I keep this as Boolean? So I say public Boolean. I'm going to search for this root, and then what I'm going to do is if I get the value as true. So if blocks we are right key not found because of the find go under recursion. Yeah, correct. It's going to then go around and iterate everything. It's not going to return you anything. So how about if I keep this as Boolean? As of now, this is what I'm thinking. Uh, let's say I keep this as Boolean will be okay. Mm, or I could just do is if let's suppose if I say if it's greater than, then go at get left, and then else it's just gonna do the right Boolean. Or maybe what I can do is rather than returning these stuff, but it's gonna give you try if an else statement for key not found. Oh, 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 oh. What do I want to do up here is, let's say on a search key, I give it the key, it's gonna iterate, so it's gonna go around and it's gonna say in the first if we can print the value, but what if it doesn't? What if it doesn't? It's returning every time, right? So if let's suppose even if I do return root and okay, so what I can do up here is let's say uh, I say s out. Let's say key, the key that you have. I'm just going to call this found, and then I'm going to return, let's say, the root. Okay, and then what I'm going to do is, let's say if I come here and say pst dot search, let's say 5. Let's take this up for an instance. So this typically should give me 5 found, or maybe no, missing return statement. Yeah. Oh, sorry. Just gonna keep this void. I changed it, but I didn't made use of this boolean. I'm going to go and run this up. Public void search key, int key, and then you're gonna give the search key to node, and what you can do is just say root equals missing return statement. So missing return statement. So what have I done wrong? Is going to return the root. Just 1 second, huh? Most probably this should work. Or maybe what I can do is, if let's suppose if it's not, yeah, this would be a better approach. If let's suppose if I get rid of this, how about now? Because there could be only 3 possible situations, right? Yeah, 5 found. Got it. So if let's suppose if I give it not 5 or maybe something else, it's not gonna give me anything. Let's suppose I would give it as 11. It's not gonna give me anything. But this code could be done in a better way. Yeah, it's gonna throw you an error. If you're gonna send it something like a very weird thing, if let's suppose if I pass this as 10, it's gonna work extremely fine. I was gonna just say 10 found, but I could do something if I want. Okay, so I'll have to change the whole scenario of the situation. I'll just have to keep it Boolean and then go around and check for if and if. But as of now, I just hope this whole situation of search makes a lot of sense. That how I'm making use of it. I just hope it makes sense now. Search is pretty much okay. So you can go around and bend around at how the return type is going to look like and how you're going to check in the main method and stuff. You can definitely can do that. You can create this as a Boolean stuff, and then you can make use of it. But there is one more thing that I want to discuss, if you allow me. There is one very important part that I want to discuss, which a lot of people generally lack, is the deletion part. Should we go around and talk about that? Other people, if you okay, so if you only say yes to me, then only though I didn't had any idea that I'm going to talk to you about deletion part, but if you allow me, we can definitely can go around and talk about deletion. Should we? Okay. Deletion. Okay, for deletion, I'd be really kneading up your brains. Okay. Why? Because this is going to give you a lot of pain, to be very honest. Like doing deletion in the BST is not really that straightforward. But okay, let's figure that out. Let's see what could be done. Okay, let's first talk about that. What could be the possibilities where you say, okay, fine, you're going to delete certain stuff, right? Let's talk about that. Everyone's here. Shall we start talking about the deletion part? Guys, should we start talking about the deletion part? Okay. All right. So what I'm going to do, I'm going to take a very simple example, a very layman example. Again, a lot of attention is what I'm seeking for. The reason is that this is going to be a little pain because there is certain things which I want to tell you from interview point of view and from the development point of view, that what we're going to code and what we're going to have a look on. Just have a look. If let's suppose if we have a very simple, not so simple, but let's suppose we have a BST. Let's say I have a BST starting from 70, then I have, let's say 30, then I have, let's say 10, then I have, let's say 40, I have, let's say 50, then I have, let's say 5, let's say I give it as 100, so I give it as 80, so I give it as 120, and let's suppose it has a left of 110. Okay, so this is the small little tree that I've built for you. Okay, now just have a look. What do you want? You want to perform a function. You want to build a function, let's say a delete called a function called as delete, which is going to take a certain value. There is going to be a value, and that value is going to get passed onto this delete function. And this delete function is going to do what? It's going to delete that up from the BST. And what you need to keep in mind that after deletion, when the deletion is all done, the properties of BST should not violate or should remain same. Should remain same. That's what we want. That okay, yeah. One more thing. One more thing. Guys, okay, what do I want you guys is to give me random numbers first. I forgot to tell you about this, but this is really important. I just want you guys to give me really random numbers. Really random numbers. 22. Okay, 22. 22. 45. 45. Let's say 37 and 51. 30. That's all I want. 37, 51, and 53. 37. 37. 51 and 53. That's it. 51 and 53. Let's say. I'm going to show you real good stuff, which is going to help you if you're going to go with insert of search in order. Just have a look. If I do the BST dot in order, just BST dot in order, what has happened? 10 found. is, oh, why have I written this as a search? I'm sorry. Insert, insert, just 1 second, insert. Sorry, my typo, I didn't had a look on it. But anyways, just have a look. Just realize and understand what's happening if you're doing in order. Just have a look on the random data. Did you figure something out? Exactly, it's gonna give you sorted orders. Very, very important. Write it somewhere, keep it in the mind, whatever. In order traversal in a BST, it's always gonna give you sorted data. Always, always, no matter what kind of like a random data you're going to talk about. But the very important stuff for your BST is going to be that it's going to organize your data in such a way that if you try to figure out that how your in order is going to go, that in order is going to come out to be as a sorted data. Everyone can just have a look. This completely random data, right? Insert that data in the BST, find the in order, and you're going to get perfectly arranged data in the sorted order, in the ascending order. Everyone can see this 5, 7, 10, 22, 37, 45, 51, and 53. Sounds okay? Guys, sounds okay? Yeah. Now, why have I showed you this? And what was the purpose of me showing you this? The purpose was that I'm going to talk to you about, do you want to hear about one of the competitive programming questions that was asked twice in Amazon, I guess once in Apple and 2 or 3 times for, but like it's one of the very, very popular question that you can come across if you're talking about BST. And this is what you call this is naive approach and a naive's problem, but I'm going to talk about that. If let's suppose, what do I have is this. If let's say I have, okay, do you want to have a look on it? Rather than just getting into deletion and stuff, it's more important that we focus on the competitive part. If you allow me, we can discuss about this. We can hold on to this deletion part. Maybe we can cover that out in the next seminar. But as of now, can we figure out on competitive part? Cool. So what I'm going to do, let's say and even if you want, I can code this up for you, right? What's going to happen that if let's suppose you are given with a pre-order data, just listen me out. What do I want? I want the pre-order as the input. Let's say the pre-order comes out to be, let's say 10, 5, 9, 13, 20 and stuff like this. Let's suppose this is the pre-order. And after the pre-order, what do I want is the in order and the post order of the data. Can you do that? Just think about it and tell me, can you find out the in order in big O of maybe n? Or maybe I can even do that in big O of 1, to be honest. Can you do this? This is one of the competitive programming questions that you can think of. I have a pre-order. I want to convert this out in the in order. And then I can want to convert this pre-order into the post order of a BST. This is the in order, pre-order, post order of the BST. Can you come out with any solution? This could be a complete random solution. Think about it. If let's suppose if I want to do what? I want to give the in-order traversal, depending upon what the pre-order traversal is, looking into the pre-order traversal, I want to give the in-order and post-order traversal of this BST. Can I do that? Let's talk about this way. I have a pre-order and I have to give the in-order and post-order. Think about it. Can you come out with any solution? Any solution, randomly. Guys, quickly, think about it. What is post order? In order, pre-order, and post order. We have talked about this in the previous session. Ishita, were you there in the last session? Were you there in the last session? Good, very good, Rashi. Very good. You're going on a very right note. Guys, everyone, just figure something out. Post is, yeah, post is what you call this as left data right. Oh, sorry. This is left, right, and data. So you go to the left, then you go to the right, and then you go to the data part, the node part. This is called as post. Anyone who could think about any of the possible situations? Think about it. No one? Now just try and figure that out. If you talk about a pre-ordered traversal, we have talked about this. The first thing that gets displayed in the pre-order traversal is what? The first data in the pre-order traversal. Tell me. The first data in the pre-order traversal is the root. Everyone? It's always going to be the root. Now, if I want to do something like this, if I say I have a root, can I not build a tree? Can I or can I not build a tree out of all these elements? No matter what, these are going to be random. But again, if I go around and insert these elements back because I know what the root is going to be, can I not find the in order and post order of this particular tree? Right? So if I just insert this data up, if let's suppose if I say 5, then I'm going to say 9. 9 is going to be less than 10, but greater than 5. So definitely it's going to come up and pop up here. Next data is going to be 13. So it's going to be on the right. And if let's suppose if I have 20, it's going to be something looking something like this, right? And now if I try to figure out that how the in order is going to be, can't I find the in order for this particular tree? It's going to be 5, 9, 10, 13, 20. And if I talk about the post order, you guys tell me what is going to be the post order? The post order is going to be what? Tell me. Left, you do not have. Right is going to be 9. Then the data is going to be 5. Then it's going to go onto the left. Then it's going to go onto the right. It does not have a left, but definitely has a right. So 20, 13. The last is going to be 10. Got it? So if let's suppose if I say you have a competitive programming question where you're saying that, okay, I'm given with a pre-order, what you need to find is in order and post order. Can you do this now? Can you sit around and code this? Depending upon what we have done in the session today. Can you do this? What you need to do is renovate your insert function in such a way in which you have to build a function called as build tree. And that build tree is going to give you all the values, right? You build this tree, and then you can go around and figure out that what your in order, pre-order, and post order of this is going to be. Does this make sense? Quickly, everyone. Does this make sense? Guys, yes, no? Guys, yeah? Cool. Now, the problem here arises that I gave you a question where I said that the in order that I want is going to be in big O of 1. How can I do that? How can I do this? If I say I want the in order in the running time complexity of big O of 1, anyone who could think about this? Anyone? Yeah, sure, Aradhya, sure, you can go around. Guys, anyone who can come across with, if let's suppose if I want to do big O of 1 in the time of big O of 1, anyone? I told you about in order. Exactly, just contain this in the array, do arrays.sort, and you'll get the value in big O of 1. That is one of the reasons you need to keep these properties in mind. If you want to work around with these things, you need to keep these properties in the mind. I just told you that every in order, no matter how your data is, no matter how randomly your data has been arranged, what you need to do is sort these data, right? The in order traversal of any of the BST is the sorted data. And if you just see the in order is 5, 9, 10, 13, 20, how would I have got this? Just by sorting this data out. Yes or no? Can I do this in big O of 1? Yes, I can do this in big O of 1. Does this make sense now? Everyone? Cool? Okay, so we are only left with 3 minutes. So if you have any doubts, depending upon the things that we have done in the session, that is insertion and searching in the BST, if you have any doubts, you can get around to your doubts. If you are good to go, just give me a yes. And if you have doubts, you can definitely ask me your doubts. Here's a code in front of you. If you have doubts, you can ask me your doubts. And if you're good to go, just give me a yes so that we can end up with the session. Anyone who wants to ask anything about this? Anyone, anything, I'm open to questions. No one? Can you repeat the big O part once more? Okay, so big O part was this. Okay, how to contact you for doubt? LinkedIn. You can go around and follow me on LinkedIn though. I'm really active on LinkedIn. So here's a LinkedIn. If you want, you can go around and for doubts, you can definitely text me up on LinkedIn. I'm highly active on LinkedIn. So there's a LinkedIn part. Will there be a next session too? Depends on your needs and depends on how you like the session. And this session was typically by your university just because you guys said that you want the session. So if you want, we can definitely have it next time as well. We can continue, or maybe we can have a discussion on totally new technology. Maybe we can talk about full stack, or maybe we can talk about React or Angular and stuff like that. We can definitely do that as well. Even if you want, we can have talk about will we have the recorded lectures? Yes, you will have that. If you go around onto the page of, okay, so I'm just gonna stop the share for a while. I'm gonna give you the link. So all the recorded videos goes out there. So I'm just gonna open my YouTube to give you that. So okay, so in the chat section, I'm going to throw you out with a link, and you can go around onto this channel, which is typically CipherSchools, and you'll get all the recordings for this recording as well and the previous recording as well. You can go around and have a look on that as well. One thing which I want you guys is to fill this poll up, depending upon how did you like the session. And this is kind of like a feedback for us. If you like the session, go around and do that. And we can definitely have more sessions like that. I just hope this poll is available in everyone's screen, right? Just push these polls really quickly. I cannot see these polls. I have no idea what you're giving it, but be honest with the feedback, because this is really important for us. Other people, just quickly fill the feedback forms, and then if you'll be having doubts, we can cater on to your doubts, and if no, then we can end up with the session then. Other people, just quickly push these polls so that we can move ahead. Really thank you for paying attention, Abhishek, Ishita, and lovely having a session with you guys as well. All right, so thank you so much for these lovely feedback. And okay, so again, do you have any doubts? If you have any doubts, I'm open to the doubts. If you're good to go, just give me a big yes so that we can end up with the session. Yeah, cool. So that's all. If most probably we're gonna meet next time as well. Depending on that, we can. Okay, one thing more. Do you want to have a look on any other things apart from competitive programming and data structures? You want to stick to this? Any new technologies that if you want to talk about, we are open to that as well. If you're comfortable with data structures and competitive programming, we can stick around to this as well. Completely up to you. Data structures. Okay. How about okay, yeah, okay. So can we stick to data structures and competitive programming? Let's keep it the way it's moving ahead. Most probably, if we'll be having a new session next seminar, we're gonna carry on to this further, and we're gonna talk about more in trees and more of the data structures part. Sounds cool? Sounds okay? Yeah, cool. So that was all for today's session. Thank you so much for joining. I hope that you would have loved the session, and we're gonna meet the next time. All right. Bye bye, guys. Bye bye. Thank you so much for joining. Bye bye.